Hello and welcome everyone to this new video in our series OpenGl ES. In this video, we will be adding a lighting to our scene. We will be implementing the Phong lighting model, and this model consists of three elements: ambient, diffuse, and specular. So one general property of the matters that we see in our world that the color of the matter is decided not only by its own color, but also by the color of the light coming to it. So this interaction of the incident light with the material, where the material will absorb a part of the incident light and will reflect some of the light. And what we will see is actually the reflected light. So the Phong model consists of three elements. The first element is the ambient. And this ambient element, you can think of it as a light source which comes from all directions and also will be reflected in all directions. So basically it has no directional dependencies, not on the incident light, not on the reflected light. And using this ambient component, we will be adding a constant color to our objects. Then we have the diffuse element. The diffuse element depends on the direction of the light source, as you can see here in this image. So this image here represents the ambient, where, as you can see, I did not put the light source and the reflections of the light are in all directions. Here we have a light source which emits in all directions. However, regarding our surface here, the light will come with a certain angle to the normal of this surface. And this angle we call the incident angle. And then this light will reflect in all directions. So the reflection of the light in any direction is the same. However, the strength of this reflected light depends on the incident angle, which, as I said, the angle between the line connecting the incident point and the light source with the normal of the surface at that point. And the strength will be higher the smaller this angle is. So when this angle is 0, so the light is coming in this direction, the diffuse component will be the largest, and if it's coming with 90 degrees, it will be basically 0. That's why we will use the cosine of the incident angle as a representation for these strings, because the cosine will be 1 when this angle is 0 and 0 when this angle is 90 degrees. And the third component is the specular light, and this what gives the surfaces its shiny properties. And for this element, the strength of the reflected light depends on the angle between these two lines here. This first line here is the reflected light, and this line here is the line connecting our camera or the viewing point to the considered point of the objects or the current fragment which we are rendering if you want. And if this angle here is very small, if it's 0, so in case, for example, we are viewing this object from this side here, from this direction here, then the specular component would be the largest, because as you can see, so we have the incident light with an incident angle I, and then it will be reflected with the same angle. So here, as you know, the reflection angle is equal to the incident angle. Then we are looking at this point from the angle where the most light is reflected, and then the strength of the light will be the largest here. So again, here we will use the cosine of this angle then as a representation of the strength of the component, since the cosine will be larger when this angle is 0. Now, as you've seen in the previous slide, we talked a lot about the normal and the incident angle, which is the angle between the coming light and the normal of the surface, and the reflection angle also. You've seen that we need this normal of the surface to compute the incident angle and the reflection angle. So now we need an extra component for our objects, and this component is the normal. And we represent the normal as a vector of 3 components, so the x component, y, and z component. In this video, I will be continuing on our previous example where we have the Earth rotating around the Sun, and I will be using the Phong model to render the Earth. And since we represented the Earth as a perfect sphere, computing the normal is not actually difficult. So the normal is only the normalized coordinate of the sphere. So if we took a cut in our sphere, it will be a circle, and here we have the center of the circle, and the normal at any point, let's say for example at this point here, is the line extending from the center of the surface, is along the line extending from the center of the surface to this point. This would be here the normal, and we'll take it norm to be 1. So we only need to take this point and normalize it. In the future videos, I will be adding another attribute to our buffer, which is the normal, and we will need to fill this attribute. For computing the lighting, we will use the world coordinates. And if our object is somehow rotated or translated or scaled in the view, we need to transform the normal accordingly. However, since the normal is vector 3, we cannot use the model matrix to transform it directly to the world coordinate. Instead of that, we will be inversing the model matrix and then transposing it, and we'll take in a sub matrix of it, which is the upper part. So since the world matrix is a 4x4 matrix, the inverse and transpose will also be 4x4. So let's imagine that this is our 4x4 matrix. We have 4 columns, 4 rows. Then this mat3 here will take a matrix which is 3x3, representing this part here from our matrix. So basically the last column and the last row will be dropped. If you want to read more about why this transformation here is used, I found some information here in the Stack Overflow and also in this link here. Let me open this link. So the main reason for that is the scale. So if we are translating, the norm will not be changed since it's directional vector. No matter where you transform it, it will be the same. When you are rotating, we need to rotate it with the same angle. However, the problem comes when we are scaling. Imagine now we are stretching this sphere in this direction, and then the norm at this point here will become closer to each other, where they will be here going more away from each other. This page contains more information about this if you want to investigate more. So for implementing the Phong model, we will be representing the objects using materials. So in our fragment shader, as you can see here, we will define a structure. We will call it material, and the structure contains a component for the ambient, for the diffuse, and these two here is for the specular. And for the light source, we need to know the position of our light source. We need to know the ambient color, the diffuse color, and the specular color of our light. And the final color of our fragment will be decided based on these components and the corresponding angles, as I explained in the previous slides. In this link, you can find different materials and these ambient, diffuse, specular, and shining components of these materials. Let me open this link for you. So you can see here different materials: pearl, obsidian, gold, copper, plastic, with different colors. And for each one of these, we have the ambient, diffuse, specular, and shining. Where the ambient, diffuse, and specular each has 3 components, the shining has only 1 component, and it will represent a power of our specular color, as you will see in the implementation. And now here in this figures here below, you see our model in 3 cases. So in this first case, we only have an ambient component. You can see that the lighting of the earth here is the same from all directions, since this ambient component does not depend on any direction. In the second one, I have a diffuse component which is large and an ambient component which is low. And you can see that the highest light is at the side of the earth which is facing the sun here, basically. And now if we added a specular component on top of that, you can see that this shining surface here is like made of a glass or a metal. So let's jump to the code and implement this. So this is our model from the last time where we have the earth rotating around the sun. Let us now go to the sphere object where we implemented our cube map texture, and that's what we are using now for the earth. So as you can see here, we are using the cube texture normal program. So let's open the corresponding shaders. So in the vertex shader, I will be adding an output. I will call it out normal. This will be used to send the normal to the fragment shader. And for computing the angle, we will also require the position of the fragment. So let me add an output also for that. And since we will be using the world coordinate to do the lighting, then you can see that the fragment position will be taken only as the position multiplied by the model matrix. And for computing the normal, we will be only normalizing the position. And then the final step is to transform this normal with the same transform, a model which is used for the position. However, remember now we need to use this inverse transpose and then throwing the 4th column and row. And that will give us our output normal, which we will send to the fragment shader. Then in the fragment shader, here is the most work of the lighting will be done. So first we need to add inputs to get the fragment position and the normal. Then we need to add the definition of the material and light as I shown in the introduction. And then we need 3 uniforms. This uniform we will be filling from the Java code. So first one is the camera position, which is needed to compute the specular component as we've shown in the slides. And we need to define a material, the material of our object, which is the earth in this case. And then the properties of the light source, which is representing the sun in our case. As before, we first start by computing the fragment color. We will not change this, and that's by using this cube sampler. Then we compute the ambient component of the light. This is the simplest component, so it's simply the ambient component of the light multiplied by the ambient component of the material. So these are both a vector 3. So now imagine that the light source is white. So we'll have ones on all three components, red, green, and blue. And the material is only red, so it's only have one on the red and zero on the other. So this multiplication will give us a red color. And this makes sense since the material will absorb all components of the light except for the red. And then let's compute the diffuse component. So the first step is to normalize this out norm, which we get from the vertex shader here. In case that the resulting norm after this computation is not normalized, we get it now to a norm of 1. And then we compute the light direction. So the light direction is the position of the light minus the position of the fragment. So it's the line extending from the fragment position towards the light. And then we compute the cosine of the angle between the norm and the light direction. And for that, we use the dot product. So remember, the dot product of two vectors is the norm of the first vector multiplied by the norm of the second one, multiplied by the cosine of the angle between these two vectors. And since we normalize these two vectors, so the first two components of the dot product now are 1. And then what's left is the cosine of the angle between these two vectors. This dot product will be smaller than 0 in the case that the angle between the norm and the light is larger than 90. And for that, we don't need any lighting here. So that's why we use this max and we put it to 0 in that case. So now similar to the ambient component, so the diffuse component would be the diffuse component of the light multiplied by the diffuse component of the material. However, here we multiply by the cosine of the angle since we have this directional property of the light. And then we have the specular component. So for the specular component, we want the view direction, which is the line connecting the fragment position to the camera position. Then we can compute the reflected light direction using this function reflect. And here we negate the light direction because the reflect function expects the light direction to be from the light position towards the fragment position and not the other way around as we did here. And now we have the reflected direction. We can compute the angle, the cosine of the angle between the view direction and the reflected direction. And again, we put that to 0 if it was negative. And the final computation in the specular is to raise this cosine of the angle to the power of the shining. And now we have the strings of our specular component. And computing the specular component is simply the specular component of the light multiplied by specular component of the material and then scaled to these strings. And now having computed the ambient, diffuse, and specular component, we need only to sum these three components and then our fragment color will be the color of the texture, which we computed here. So it's already saved in fragment color multiplied by the Phong out. However, since this is a vector 3, we need to convert it to vector 4 and the alpha component here will be 1. That's all what we need to do. And now if we run our program, you will see the earth is appearing black because we did not set any of these variables which we are using here. So that we can do here inside the sphere object. So again, we have here only one attribute, which is the position. Later, as I said in the introduction, we will add also the norm and of course a texture or a color as needed. In the draw as before, we use the program and we bind the buffer and the texture, and then we are setting our matrices, the model, view, and projection. So I will add the light and material properties after that. So here after we set the projection, we put the light and the material properties. For that, we will be using the name of the variable, as you can see here. So we have the variable called light, then point the property which we need to set. So here we are setting the position and we are putting that to the light position. This position is in the origin since in our case the light is coming from the sun and it's in the origin of the coordinates, so it's in this position. And then for the camera position, so this variable here, we will be using the scene get camera then get position. So I will need to implement these two functions here, as you can see. I will do that later. So now for defining the light properties, I'm defining a light color which has a red component of 1 and green of 1. 0 on the blue. And then for the diffuse and ambient colors, I'm making a copy of this, so it will be the same. It will be also 110, the components. And then I'm scaling them here. Let me, as a beginning, make the diffuse color to be 0 and let the ambient color be large. Then I will set those ambient diffuse as defined here and also set the specular. Let me make the specular also zeros here. Let me define the ambient and diffuse in the same way as we did here for the specular, so don't confuse you. Now we don't need these lines here. Now for the material, we also define the ambient, diffuse, specular, and shining. And that's it. We only now need to implement these functions. So let us go to the program. And we need to add two functions. Set uniform 3fv, so this is setting a vector of 3 floats. Same as the other functions, we need to get the uniform location and then use a specialized GL function to set the value of this location. Same here for setting one uniform float. And in the camera, we need to add this function get position. And this function will just return camera position. And since we are inside the camera, let me refactor this. Since we are inside the camera, no need to put cam here in front of it. So we return the position. And that's it. Now let us run the code. As you can see now, we have an ambient color from all directions. So it looks like before, since this color is the same all over all three components. If we make it larger, then the light will be more apparent on the earth. If we made it also smaller, you can see that the earth will become darker, but still you can see it. Yeah. So let us put the light to a yellow color since the sun is yellowish. And now let's say that the earth reflects the blue and the green component perfectly, but not red. And you can see it appears now green because when we multiply the light ambient component by the material ambient component, the only non-zero component would be the green. Let me put this back to 1 and make the ambient component to be very low. And let's put it the same in all colors. And now let's make a diffuse component and let's put the diffuse component of the light to also yellow. And let's assume that the earth reflects all colors. And let's rerun. So now you will see that the part of the earth which is facing the sun is getting most of the light. You can see it here. Let me make the ambient even smaller so you can see the effect more. And now let's make the specular component the largest and see how the earth will become shining. And let me not change the light. Let me just change the material actually. So keep the light to be yellow in all components, and then here we'll make the ambient component small, and let's let the specular component the highest and rerun. And you see now this shining here. Now if we made this power higher, you will see that this spot here will become more shining, having more specular from this spot, but then will become also quickly darker when we go away from this spot. So let's make this smaller. And you will see that this spot will become less shining, but also wider. Now let's put this back to 20 and raise our specular component and our ambient component a little bit, so we can even see the side of the earth which is far away from the sun. And let's rerun. And now you can see the effect of all components. So even here from the side of the earth which is away from the sun, we can still see something because of the ambient color. And on the side facing the sun, we can see it has more light because of the diffuse component, and of course it has this shiny effect here because of the specular. And that's it for this tutorial. I hope you like it. Please give it a thumb up and subscribe the channel. And I hope to see you in the next video. Bye.